I'm going to give a brief introduction to dynamical systems in the plane in this video. Essentially, we're going to be looking at what happens if you have a pair of differential equations that are coupled like this. So the derivative of x is some function of x and y, the derivative of y is some other function of x and y, and in this case the independent variable is time t. In general, there's no symbolic solution to differential equations of this form. Instead, we're going to be developing tools for geometric qualitative solutions to this kind of differential equation. We'll be interested in what is the long-term behavior. Is there something as simple as maybe convergence to an equilibrium? Does the value of x oscillate, for example? So there's a lot of different things that a dynamical system like this can do. But before we can get into the full theory of what's known, we need to handle a sort of basic case, which is that suppose we have just a linear system of differential equations like this. We can abbreviate this by just letting x with a vector symbol over it stand for the column of x and y, and let A be the matrix A, B, C, D. A couple of things to know about this kind of equation. So first of all, the origin is a fixed point. That's because if you simply define a solution that x of t equals 0 always, that satisfies, well, its time derivative is 0, and a times x will always be 0, and these, by the way, are 0 vectors. So the 0 vector is a constant solution. We can look to see whether it's stable or unstable, and so we can talk about stability of the origin. That is, do nearby solutions converge to 0, or do they grow? Or maybe they have other possibilities. It is possible, for example, to have solutions that just trace out a circle if the A matrix has the right properties. Another thing here is that the solutions to x dot equals ax form a vector space. We've already seen that the origin is a constant solution, a fixed point. That's important. There has to be a 0 in order for a set of things to be considered a vector space. But if we had two solutions, so suppose x1 and x2 are both solutions, well, then if I let x3 equal the sum of x1 and x2, its time derivative is the sum of the time derivative of x1 and the time derivative of x2. Both of these solve the differential equation, so their time derivatives are the matrix A times the vector function x1 and x2. And since matrix multiplication is linear, I can factor out the matrix A to the left and then arrive here, so that the derivative of the sum is A times the sum function x3. So this sum function is also a solution. So that means that the set of solutions is closed under addition. And furthermore, if I'll call it alpha is a scalar, which for our purposes is going to mean a real number here, well, alpha times x1, well, let me do it like this. I'll write it with Leibniz notation. Alpha x1, the derivative of that with respect to t, well, I can take the scalar alpha out and get alpha times x1, sorry, alpha times x1 dot, which is alpha times a x1, because x1 is a solution, and then I can push the scalar through. So then, oh, I forgot to give it a name. So then I'll call it x4 equal to alpha x1 is also a solution. So we have proved that by adding functions in the obvious way and multiplying by scalars in the obvious way, the set of solutions to this linear differential equation is closed under addition, it's closed under scalar multiplication, it has a zero element, which is the zero function, so that's what you need to confirm that it's a vector space. I won't get into all of the theory here, but in 2 dimensions, the space of solutions has 2 dimensions as well. Which means that if we can find any 2 linearly independent functions, x1 and x2, that satisfy the differential equation, as long as we found 2 linearly independent solutions, all other solutions can be expressed as a linear combination of those solutions. So any 2 linearly independent solutions form a basis for the set of all solutions. I guess I should call it a space, for the space of all solutions. So in follow-up videos, I'm going to explain how you can start with a matrix, do some analysis on it, and determine whether the origin is stable or unstable. And in between, we'll have to do calculations involving eigenvalues and eigenvectors. We'll also have to dip into complex numbers. There's a lot to all of this, so I've split it up into a lot of follow-up videos, each of which is not too terribly long.